Okay, thank you. So yeah, I'm Jussi Leinonen currently at MeteoSwiss. I used to work with Alexi Bern at EPFL, and before that at NASA JPL, where I got interested in this topic of using generative adversarial networks for modeling atmospheric fields. And the organizers asked me to give a bit of an overview of machine learning techniques that might be useful for atmospheric science. And so we'll start with that, and hopefully by the end of that, we'll also have a little bit more tools to understand what's going on in these GANs, because this is a bit of a complicated topic technically. So what's a neural network? In the old days, people used to really emphasize how neural networks were kind of emulating the way that the human nervous system worked. But in the recent years, that's been de-emphasized a little, and now we're really talking of neural networks more in terms of series of these fixed mathematical operations, which are typically called layers. And these layers have trainable parameters, and then the whole network has some kind of a training objective that we try to minimize. So the objective can be, for example, the mean square error of some target variable. And the two fundamental types of layers that we see in neural networks are these affine transformation, which have basically a trainable matrix and a trainable bias term. And then the other fundamental type are these nonlinearities. So one common one is this hyperbolic tangent. In modern machine learning, we use a lot this nonlinearity that's called rectified linear unit, which is simply a function that's an identity map when it has a positive input, and it returns a 0 when it gets a negative input. And for these layers, but really for all layers that you put into neural network, one fundamental property is that they are differentiable, or at least piecewise differentiable. So we can compute analytically the derivative of the objective with respect to each trainable parameter. And this means that we can optimize these parameters using gradient descent. And one nice thing to note is that these packages that are usually used to implement neural networks can do automatic differentiation. And this is implemented, for example, in TensorFlow and PyTorch. And this means that you don't have to compute these derivatives manually. The libraries will do that for you. So the simplest neural networks just repeat these two most fundamental operations that we listed in the last slide. So these dense affine transformations of this type, and then the nonlinearities. And a deep neural network, and hence the term deep learning, is a network where many of these layers are used in sequence. In modern times, we might have networks of as much as hundreds of layers. And the idea is that each trainable layer learns higher level features than the previous one. And just for ease of notation, because like, for example, in this network here on the right, we keep repeating these same units. We often describe these networks in terms of blocks. So here is this same network. Here we can describe that like this. So repeating this, what I call here dense block. So we have one dense affine transformation and one nonlinearity in each of these blocks. And so most of you have probably heard of these convolutional neural networks. And in these, we simply replace these affine transformations with convolutions. So now our inputs are typically images, and we do a convolution and then a nonlinearity in a single block and keep repeating that. And this kind of network structure that I'm showing on the right here is image to image. So we would input an image and output an image. And actually, this is not a very good way to make an image to image network, but we'll get back to that. To improve our processing of images, we have to introduce another type of layer, which is called a pooling layer, which is used to reduce the image size in a way that we take local regions in the images in each processing block. And then for these local regions, we take some statistical property of that region and then assign it to a single value. So here, for example, we are taking a max pooling with 2x2 regions. So we are dividing this image into blocks of 2x2 pixels, and then we're taking the maximum of each block and then assigning that to the output image, and that way the size of the image is reduced by half. So for example, we could start here with an input image of 32x32 pixels, and then we go down to 16x16, 8x8, and 4x4. And typically what we do at the end is then we would pack that information that we get after several of these downsampling blocks into one more dense layer, and then out of that get some kind of class for the image. So for example, we could have an set of input images that might have a cat in them or might not have one in them. And then we would train our network to output 0 for no cat or 1 for yes, there is a cat in the image. And the network would learn to optimize these convolutions in a way that it would maximize its chances of detecting a cat in the image. So this brings us to a way of processing these images in a little bit smarter way. So we can take these downsampling blocks we defined in the last slide. So with convolution, nonlinearity, and then pooling. We can use these to build this kind of encoder-decoder networks. So here we take an image and then we run it through a couple of downsampling blocks, then typically some convolutions, and then we do an upsampling step back to the original size of the image usually. So the upsampling block has an upsampling operation where we increase the size of the image, and then we do a convolution and a nonlinearity like in the other blocks. And this way we get an output image that is the same size as the input. So in this example, for example, if we keep using the cat example here, we could have images of cats here, and the output image could be a map of basically a binary map that would show the pixels in the image that are part of the cat, and then another label for pixels that are part of the background. And from these encoder-decoder architectures, we get to the so-called autoencoders. So here we add to this previous architecture here in the middle a convolution. Between the convolutions we add this this bottleneck, which basically drives the data processing through a very small amount of information. And then we optimize this network in a way that we try to get the output image to match the input image as much as possible. And so this forces the network to learn kind of the essential properties of the input data set. This enables us to do a kind of unsupervised learning with neural networks, and then we can kind of use this the contents of this dense block in the middle as a kind of a result for the unsupervised classification. So, for example, we could use this kind of data set, which is very commonly seen, which has handwritten numbers, and if we build a good autoencoder this, we could hope that the features that we have in the bottleneck correspond to the different types of numbers. Say if we have 10 different hidden features, they might correspond to the 10 possible numbers that are in them. Okay, so we're getting close to the end of the introduction, but I'd like to introduce a couple of important concepts here. So one thing I want to talk about are the residual blocks, which have been quite common in the recent years. And these include a skip connection in the network. So in addition to these convolution blocks, we basically pass the input through, and then we add that back to the output of these convolutions. So basically that means that these convolutions just learn the residual of the previous block. And this means that the network can pass data through layers that we aren't using, because it's fundamentally quite easy for these blocks to learn just to do nothing if these blocks are not needed. And this in a way solves or at least helps solve the problem of that we don't really know how many layers we would need to have in our networks, because in this kind of residual setup we can have a large number of layers, and then the layers that we are not using can simply remain inactive. And this also means that the optimization gradients are better preserved, which can sometimes be a problem with very deep neural networks. And indeed, these residual networks have enabled people to build much deeper networks and still be able to keep training and optimizing them. We can have hundreds of layers in a single network. And another thing I should mention are these recurrent units. And this is a very complicated topic that I don't have much time for, as you can see on the diagram on the right, which is for the so-called LSTM implementation. But the key thing to know about these is that they learn the update rules between time steps, so we can model time variable data. And these are most commonly used in, for example, natural language processing, but there are also implementations which are for images evolving in time. So these are implemented using convolutions, and these can be used to do kind of video processing, or in our case, to do processing for time evolving atmospheric fields. So we're getting towards the generative adversarial networks, and these are generative models. So what does that mean? A generative model is typically contrasted to a predictive model, which means that we have basically a neural network, for example, can learn a mapping from the input space to an output space, and then it's usually completely deterministic. Whereas with a generative model, we can learn to produce samples from a distribution, and particularly with the conditional generative model, we can have an input, and then we can model the conditional distribution of the output variable with respect to that input, or conditional to that input. So it means that we might get multiple answers per input. So uncertainty is modeled, which is very interesting for our field, although it's kind of ignored in some others. Here is an example slide of generative adversarial networks. So we're finally getting to them. You have perhaps heard the term deepfake, and GANs are one of the most popular methods for generating these so-called deepfakes. So basically images that look very real, but are actually not real images. So for example, in this this figure here on the left, all these faces here are computer generated. They are not real people. GANs can also be used for things like domain translation. So here in the middle, we have a few examples of, so on the top row, we are turning photographs into paintings that look like the photograph. In the middle row, there is an example of turning horses into zebras. And in the bottom, there is a network that has learned to transform landscapes from winter conditions to ones in summer conditions. And then a final example here, we have infilling. So we're taking images that have part of them missing, and then we have the GAN try to fill in the missing part of the image. So how do these work? GANs are a setup of two competing neural networks, usually convolutional ones. So we have a discriminator, which is kind of a binary classifier network that tries to distinguish real samples from our data set from generated samples. And then we have another network called the generator that tries to output samples that the discriminator considers to be real. And this way, the generator learns to generate realistic looking samples. So if we consider that the neural networks are quite powerful image recognition machines, then if we are able to fool the neural network with with the generator network, then we would expect that the generator outputs are also quite realistic. So the generator network is, like all neural networks, completely deterministic operations. So how do we generate different examples from a probability distribution or for the sample distribution? And so the way we do this is that we have this noise component. So the generator takes an input of some random variables. It's usually could be, for example, independent Gaussian random variables. And so we can see this generator as a kind of a map from the probability distribution of the noise to the probability distribution of the data. And the important thing to realize about this is that the data distribution is typically highly complex and highly spatially correlated in the case of images, whereas the noise distribution is very simple, as I said, typically independent, identically distributed variables. So we're able to map a simple probability space into a very complex one. And then a straightforward extension of the generative adversarial network is this conditional GAN, which includes one more thing in the network framework, We add this condition, which is passed to both the generator and the discriminator. And then we are instead learning this map from the distribution of the noise and the condition to the conditional distribution of the sample conditional to this condition variable that we're passing. So this is where we're kind of getting to a place where these conditional or where these generative adversarial networks are getting kind of interesting for science, because in science we have these conditional probability problems just everywhere. So for example, we could be inferring some quantity x from some other quantities y. So for example, inside a model to try to get the probability distribution of one variable when we know some others. We could try to do a retrieval from measurements. So get some physical quantity x from some measured quantities y. Or we could try to predict the future state of some variable from its current state or its past state. We could try to go from from a low resolution field to a high resolution field, so kind of do downscaling. And we also often have problems where our data doesn't cover spatially all the space that we have. So we could try to model a complete data set from incomplete measurements. And these are all underdetermined problems, and conditional GANs can learn to generate the distribution of solutions of the target variable with respect to the inputs that we have. So let's get to the first concrete example here. This is from a data set of co-located cloud observations. So this is from work I did while I was at JPL. And here we have co-located some cloud variables from the MODIS spectrometer. So this is things like cloud optical depth and cloud top height. And then we have these cloud vertical profiles from the CloudSat radar. And what we were trying to do here was to train a conditional GAN to generate the CloudSat vertical profiles based on just this MODIS data, which is effectively one-dimensional. And so here are some results. So in the top, we see the cloud properties from MODIS. In the middle are some generated profiles from the GAN, and the real profile is shown in the bottom. So just at a glance, you can hopefully see that the generated profiles look quite realistic, quite similar to the ones we see in the set of real profiles. And let's look at a couple of these columns in a bit more detail. So from this one, we see that the conditional GAN has learned to infer the cloud height and the thickness quite well, and also the intensity of the precipitation, which is here reflected by the radar reflectivity. We're also able to detect the presence of multi-layer clouds, even though we have this MODIS measurements, which doesn't really see multiple layers all the time, but it looks like this GAN is able to use this kind of spatial variability, these sudden jumps in the cloud top height that we see in the input data to infer that there is a multi-layer cloud present and actually generate them there. And another thing we can see is that we're doing a pretty good job at modeling uncertainty. So in this case, the model is a bit more uncertain about what kind of cloud profile there might be underneath this MODIS measurements. And so it reflects that by generating more variability in the outputs. So if we look at this previous example, here there is quite a all the outputs from the model are quite similar, while here there is quite a bit of difference, especially if you look at the structure of this lower cloud layer here. So in this example here, for example, we have almost nothing in the lower layer, whereas in this one we have generated quite a thick lower layer. And so it looks like the conditional GAN has also developed some level of understanding of the uncertainty and these profiles. So then we can move on to the second example that I'm going to go to in some detail. So in this work, which we did last year, we were looking to demonstrate doing stochastic downscaling with GANs. So this kind of overlaps with some work that was presented yesterday. And so here we're trying to generate high resolution fields from low resolution inputs. And so the objectives were to generate realistic fields and to use this non-deterministic aspect of the GANs to model the uncertainty, and then to model the time evolution of fields in a consistent way, so that we can also get time evolving downscaling that's kind of consistent between the time steps. For the data set in this work, we used the MeteoSwiss operational radar data set. And here are some results we got from this. So here in the top row, we have the real examples, and then we artificially downscaled those or downsampled those into a lower resolution, and then using this as a condition to the GAN, we tried to generate higher resolution outputs, which are shown here in the bottom 3 rows. So you can see at a glance that this can generate quite nice looking outputs, and also it's clear, for example, if you look at this cloud here and this one here, those seem to be kind of 2 different interpretations of the GAN of what that cloud or what that precipitating area might be. And looking at these subsequent frames, we can also kind of see that the texture of them stays kind of similar between the frames, so the time evolution is modeled in a kind of a consistent manner. Here's another example. I won't go into details too much of this, but we can also see for another kind of complex structure of precipitation, where we have a kind of a mix of more large-scale precipitation and then some kind of cell-structured precipitation, and we see that the GAN can actually manage this quite well, that the mode of precipitations there changes in the images. And then because we have a fully convolutional architecture for this GAN, which means that we only have convolutional layers. We're not using the dense layers at all. This means that we can train the GAN with small examples, and then we can apply the generator to larger images after we've trained it. So here you can see in the middle the borders of Switzerland, and here we have applied the generator to samples that are about on the order of 700 by 400 pixels, whereas it was trained using 128 by 128 pixel sized samples. So we used smaller training samples so we can save on training time, but it appears that the generator still works just fine for the larger input images, because it's fully convolutional, so it basically just learns the scaling rules that are kind of independent of the position in the image. I won't go into too much detail about this, but I'll just remark that to evaluate the image quality metrics, we use this so-called continuous ranked probability score, which is something that comes from ensemble forecasting, and this turned out to be quite a convenient way to evaluate the outputs when we have these many realizations. And then we also borrowed another trick from ensemble forecasting in terms of these rank statistics. So what we do is basically we take the real value and we compute the rank of the real observation in the ensemble of predictions from the GAN. And we can expect that the uncertainty, if we model the uncertainty perfectly with the GAN, then this rank of the real observation should be uniformly distributed. And so we can use the metrics of the similarity of the rank distribution to the uniform distribution to evaluate whether our GAN is doing a good job at generating the right amount of uncertainty. So we can evaluate the distribution properties of the GAN in this way. And one interesting thing we found was that the image quality metrics actually converge and then saturate very quickly. But the rank metrics converge for a lot longer. So basically, you could train a GAN that generates already very good looking images, but it doesn't yet have a good idea of what the uncertainty is. But when you keep training it, it actually gets better at the uncertainty features as well. Okay, so just a brief recap of some other studies that have been using GANs recently. So this is a study of mine also from last year, where we were using a slightly different setup with GANs to do unsupervised classification of these in situ images of snowflakes. In one work that was published recently, I believe, the authors were doing rainfall disaggregation. So basically, they take a map of rainfall as a kind of a daily, the sum of the daily precipitation, and then they try to generate different realizations of what the hourly precipitation might have been throughout the day. Here is an example from one study that was generating multiple global climate data fields. And then there's another downscaling study here, which was looking at global climate model data. So they were taking this coarse resolution output from the global climate model and then trying to generate these higher resolution images using the super resolution technique. Okay, so we're getting close to the end of the talk. So I'd like to conclude with these notes for those people who are thinking if they should consider GANs for their own work. So to me, it seems GANs, and in particular these conditional GANs, are a natural fit for quite a few earth science data problems. So you should consider them if you need this kind of realistic spatial structure, and if the uncertainty aspect of the data problem is important for you, which it often is in this context of earth science data. There is another kind of GAN also that we can use to do unsupervised data discovery, like we saw in this example with the snowflakes. And in general, I think there are quite a few low-hanging fruits that are still available to pick. So if you're thinking about a topic, for example, for a PhD student or a postdoc, I think there are quite a few things where you could get pretty nice results with a little bit of effort. But regardless, when you're considering using GANs, you need to do a little bit of cost-benefit evaluation because they have quite a steep learning curve to train them, and even once you know how to work with them, they are a little bit tricky in the sense that they can just fail unexpectedly, and they take a lot of computing power to train and so on. And just for one more remark is that since we model uncertainty through the sample diversity, this is the same kind of mindset that ensemble forecasters already have. So if you are used to doing ensemble forecasting, then you already have the right kind of tools and the right kind of mindset for working with the GANs, and maybe you might even know about some methods that can be used to evaluate these conditional GANs better, because that's a topic that has received relatively little attention. So I'll end with that, and I can start taking some questions. If you're interested in discussing the use of GANs in these weather, Earth observation, and climate applications, feel free to contact me. And in the background, while I'm taking questions, I will play this video. So as I said, this downscaling GAN can generate these time-consistent fields, and we actually applied this to 1 full month of data from Switzerland. And here we can see the real precipitation field on the left, the downsampling on the middle, and the reconstructed field on the right. So thank you.